Yes, we started our discussion on chi-square. The last one, we look at Pearson's chi-square, likelihood ratio chi-square, corrected chi-square. Yet corrected chi-square. We also talk about Fisher exact test. Today, we want to look at maybe another one or two type of still chi-square. Chi-square for trend. So this chi-square for trend is used to assess whether a binary variable vary linearly through the level of an ordinal variable. It's very simple. If you look at the table, but this table, this one is more like a mathematical table. Let me use the second one that has value in it. Look at the example. The table shows the employment status among people of different level of education. Can one say that employment vary linearly along the level of education? So, like the binary outcome is the employed, not employed. Employed, yes, no. The same as say employed, not employed. So employment status is the outcome variable. When you look at relationship between level of education and employment status, you agree that it is the level of education that will determine employment status, not employment status determining level of education. So when you look at the relationship now, so level of education will be the exposure or independent variable, while employment status is the outcome or the dependent variable. So the employment status now, there are two categories of outcome there, either employed or not employed. So that's why we call it binary. Now, we want to know how it varies, the employment status varies along different level of the education, which is an ordinal variable. Ordinal means the level of education is not, you can arrange in and say, oh, one is higher than the other. It's not nominal. If we say different department now, medicine, surgery, O&G, pharmacy, these are nominal in the sense that it's just different department. If you arrange, you can decide to arrange alphabetically. It doesn't mean that one is higher than the other. It's just different department. That's nominal. But in ordinal, you can arrange them in ascending order or descending order. That's what we have now. Or for example, level in school, 100 level, 200 level, 300 level, 400. That's ordinal also. So level of education, no formal education, primary, secondary, and tertiary. Different level, you can arrange them. We know that primary is higher than formal, no formal. Secondary is higher than primary, and tertiary is higher than secondary. So it's an ordinal variable. You look at how an outcome dichotomous variable or binary variable vary along the different level of an ordinal variable. I think it's very clear now. But when you look at the table critically, what the summary you see here is what we call observed value. Observed value. The summary you see here. So from here now we have 300. 300 actually the same data set with what we used last one we used. If you remember, the number employed is 185. The number not employed 115. But here now the other one we use sex and employment status. Here now we're using level of education and employment status. So we have total 300. How many have no formal education? There are 15. How many have primary education? 85. How many with secondary education? 125. That one has the highest frequency there. And tertiary education, 75. So everything 300. So if you now look at out of 15 that have no formal education, how many are employed? 5. That's 33.3. If you put in percentage, 5 over 15 times 100 is 33.3. Number not employed is 10, that which is 66.7. Primary education, 85 of them, 35 employed. That is 41.2%. Secondary education, 80 employed. is 64%. And tertiary education, 86.7, 65 employees, which is 86.7. You may see that 80 and 65, but 80 out of 125 is smaller than 65 out of 75. And that is why so you can see you can see with your eye that as the level of education increases, the level of the employment status increases, the proportion that I employ increases also. So it's a trend. And that is a trend you want to test. This one just look like perfectly a trend, but some situation you may see that it may break somewhere. The way 33 less than 41, 80, that 80, it may be maybe let's say it's 88 now or 90% before you go to 86.7. It doesn't stop the trend. You can still test it. It's showing that it's increasing, but it breaks somewhere where the tertiary will be less than secondary. So you can still test it because it may still show trend. But this one now, by looking at it, you can see the trend. So this for educational purpose. In reality, it may not be like that. You may even see that maybe no format is higher than before the trend starts. And the trend can decrease also. The proportion may be decreasing as the level of education increase. Depends. Whichever way, we just want to see is there any trend. And that's the essence of this method, this chi-square for trend. So this trend you are seeing, is it due to chance? What you can see, the way the percentage increases with the level of education, is it due to chance occurring? If you want to put it to test, we now use this chi-square for trend. So the way to do is to first assign, it's just for us to go through and understand. If it's too technical, don't bother yourself. All you need to know is what I've just explained, just to look at it. That's the logic. Because in reality, you use a machine software to analyze it. I already told us last lecture that SPSS record this chi-square for trend as linear by linear association. Linear by linear, that's what it calls it. So, and that is why it's good when you enter your data, you label it very well. The one that is ordinal, that is a page that will show you if it's ordinal or not. That is what the computer will be able to use to bring the linear by linear for you. Now, you first assign in, how is it done if you want to solve it with that? You first assign a numerical score across the categories of the ordinal variable from number 1 for the lowest serially to the highest. So, normally when you want to give an arbitrary number, you start with number 1. So if you start with the lowest, doesn't really matter whether the distance between each value, you just say 1, 2, 3, 4, 5. So this one is 1, 2, 3, 4 because there are 4 categories. First of all, do that. So in this case now, that's what you see. The last column are attached to the table. 1, 2, 3 for each level. Then calculate the mean score for yes or no overall by multiplying the allotted score for each category by the frequency in the category. Look at it. Look at that T1 you see. I see that 1 times 5 plus, can you see? 2 times 35. Can you see? T1, 1 is for no formal education, times 5, there are 5 there that I have, that I employ, plus 2 is for primary education, times there are 35 that I employ, plus 3 is for secondary education, there are 80 that I employ, plus 4 times, which is for tertiary education, that are 65. So you just give it, you now add everything together, it gives you 575. You see, you now look for the total. Can you see now? We now do the T1, then T2 is for the, you see now, 1 times 15. Total is 15. 2 times 85. Can you see? You now do the same for the total. The first one you do is for the years, those that I employ. Now do for the total. Can you see across? So we now have 3, 1 times 4, and times 15, plus 4 times 85 plus, you can see the factor now. Can you see? You know, you are raising it to power. 1 times 1 is 1. That is 1 times 15. The second 2 times 2 is 4. That's 4 times 85. 3 times 3 is 9. That's 9 times 125. And 4 times 4 is 16. Can you see? So what you are using to multiply the total now is the square of each of this code you put there to give this. So you now come, look at, you know, it looks somehow, but that's why you may not even bother yourself. I'm just telling you the logic, the way it's Hermitage that first of all describe this, and that's why they also call it Hermitage. Yes. So Hermitage chi-square. So I'm 185 times 115 plus raised to power and going to 300. So don't even bother yourself with this or that one. So you now come, all those T1, T2, T3, V, you put in this formula, which is somehow cumbersome. And at the end of the day, give you 39.186. Now, that is chi-square. And irrespective of the level of how many level, either 3, because if you say trend, when you say something is ordinal, it cannot be dichotomous. It has to be at least 3. You have education and say no formal, you cannot use it. It has to be at least 3 before you can say there is a trend. You must have 3 classes at least. Whether it's 3 level or 4 or 5 or 6, any level, the degree of freedom is 1. The degree of freedom for chi-square for trend is always 1. So from what you can see that 39.186 for degree of freedom 1 is very, very significant for chi-square. You know that critical value for degree of freedom 1 is 3.841. And you having 39 is not significant. So the corresponding B value is going to be extremely high, low, small. So the way we run it with SPSS, we look at it. If you look at the SPSS, we have serial number. They know there are 300. Then the second column is what do I have there? Okay, sorry, because the problem here is that the data set that is the same data set we use for that. This data set is used for many things. It's not only for, so this thing sitting, unless if I decide to even run it out for you and run it for you. So because the way I press, I've already selected this thing is hiding some information that which you cannot see. But what we do is that analyze, go to analysis, cross tab, anything chi-square, except few type of chi-square there. And most of the chi-square that require anyone that require contingency table, row and column like this, you go to cross tabulation. That's where you analyze chi-square. You go to analyze, it gives you some option. You go to descriptive statistics, now go to cross tab. So you'll be able to, normally you put it, the exposure variable will be along the row. Okay, look at it. When you go, it show you, can you see? It give you education as the row. You put employee, non-employee. Can you see? Employee, non-employee. The employee, yes or no. So the name of the variable employee as the column. Can you see? Under the column. And you go and click chi-square. You click on statistics. When you click on statistics, you click on chi-square. Can you see? There are many things that are there. Chi-square. Then, because when you click on chi-square, normally it will bring basic chi-square, likelihood ratio chi-square, and chi-square for trend. Everything, bring it out. You now move. Then, okay, if you want to put the observe row color, you want to show the percentage, you click on the percentage, you click on the row to show you row percentage. Most of the time, if you have already put in your, you arrange it very well, such a way that the exposure variable along the row, the outcomes along the column. When you are running your chi-square, you select row percentage, because that row percentage, because your exposure is along the row. If you put your exposure along the column, even for this one, it will not even make sense if you are doing chi-square for trend to put your this along the column, because the exposure should be along the row and the outcome along the column. After all, for chi-square for trend is for when we have outcome of 2 categories and the exposure is many categories, at least 3 categories, which are ordinal. In that situation, it even makes sense to make it along the row rather than along the column. So when you show it, you click, this is what we give out. Look at it now. All those patterns you put there will help you put it. Now, if you now look at the statistic down, you see, give you Pearson chi-square for that thing, likelihood ratio chi-square, linear by linear association. That is the chi-square for trend, which is 39.185. And you see, that's what we get in that calculation, that rigorous calculation, 39.1. So what you need to do, you don't need to, if you are not going for, even I take postgraduate, I don't give them that type of question to answer as per to calculate the chi-square for trend. I just feel that it doesn't make sense. So we give them Pearson chi-square, something that at least let them exercise their brain. But the logic behind is I teach them how to use SPSS to run all this. That's just logic. It's just for you to know the logic. Not that you have to be, imagine cramming, you're going for exam, cramming that type of this thing. For what? If you cram it today, you forget it tomorrow, if you even use it. So, and if you cannot cram it, you may fail or score low. Someone that is able to cram it, that doesn't even know much, or maybe just or smuggle it inside and pass. So that's why I don't give it, just for you to know the logic behind it. So chi-square, you can see that this for Pearson chi-square, the degree of freedom is 3. You know there are 8 cells, 2 row, 4 row, 2 column, making 8 cells. 4 minus 1 times 2 minus 1, making 3 times 1, making 3. So for Pearson and likelihood ratio chi-square, there the degree of freedom is 3. But for linear by linear, which is chi-square for trend, the degree of freedom is 1. Surely 1. Can you see? Now let's move. Is there any question on that? We'll move to the next type of chi-square we want to look at, chi-square test of goodness of fit. Is there any question on a chi-square for trend? Okay, no question. Okay, let's move to chi-square test of goodness of fit. This one is quite interesting. Quite interesting. To me, it's even more innovative, more is something you should know very well. The other one, many people don't even bother. This trend, people don't bother much. There are many, sometimes when we analyze for people, we know that the exposure, when we look at, most of the time, our outcome variable will surely make it dichotomous, like say, knowledge, good, poor, attitude, positive, negative, you say perception, good, poor, already dichotomized. So when we try to cross-tabulate with social demographic characteristics, for when you have grouped the age, it become trend, it become ordinal. When you group age, it become ordinal. When the education is ordinal, it's all those ethnicities that are not ordinal. So there are some of them that have the ordinal something there. We usually use Pearson chi-square. But sometimes when you put chi-square for trend, even the examiner may not even, or the supervisor may not even understand. It often creates problem for the student. So you all leave it out, unless if somebody now asks for it, and do chi-square for trend. So people don't actually use it and just use ordinary Pearson chi-square for that situation, unless somebody asks for that, you want to know the trend. Now, let's look at the chi-square test for goodness of fit. is a single sample non-parametric test. We already know that chi-square is non-parametric test. Just know any chi-square is non-parametric test. So it has nothing to do with normal distribution as per you see that it's following normal distribution. No, because you are not, it's not handling numerical variable. They are categorical variable that is trying to look at association between. Even in this one now, well, start to compare categorical variable, well, the same categorical variable from two, comparing one sample with existing value somewhere. I will explain. So it's also called one sample goodness of fit test, used to determine whether the distribution of a categorical variable, e.g., ABO block group. This is one that usually come to mind. You want to determine if it follows a known or hypothesized distribution, e.g., a known pattern in the population. Let me explain. You know, in the population now, any population, work might have been done before to know the distribution of blood group, I mean the ABO blood group. Let's remove the resource out of it. Let's just focus on the ABO system. In the ABO system, we have A, we have B, we have AB, and O, 4 categories. So work that has been done, epidemiological survey or whatever that has been done before in the particular environment will show you what percentage of each, what is the proportion of each category of blood group. Maybe 20% of the population is A, maybe 15 is B, maybe another 15 or 18 is AB. Then we know that O is actually the highest, maybe 40 something or 50, but close to half or sometimes half of the population have blood group O. So 40 something, close to 50. So maybe that is what is known. And in the lab now, every time people come, they donate blood, they do blood group. So you see that you have data there. You want to know, okay, these people that come to this facility, are they representative of this population? Because those have been done before that. This is the percentage of the blood group, each category of the blood group. For this community or for this, yes, community, we want to know, okay, those people that come to facility, do they actually represent? Because sometimes they may not. For example, now people that come to tertiary, it will be quite different from people that will normally attend the PC or whatever. So you want to know these people that attend that donated blood in this facility or that attend this facility whose blood group have been determined. Their blood group is still the same. The percentage is the same of each category of blood group. It's the same with what operates in the community. In that situation now, it's easy. You calculate your own percentage in the facility. You see that it will not be exactly, maybe your own, they are saying, maybe in the population is 45 for whole and your own is 40 or 39. And so maybe the other one is 20, your own is 25. The other one that is 15, your own is 10. Somehow, you have the same different percentage. But of course, when you add each together, it gives you 100% for each of them. So you want to test. So you want to know your own. Does it fit into what is known in the population? That's what we call goodness of fit test. So you want to know if a particular distribution fits into a theoretical one or hypothesized one. Theoretical one just means that the one that has been known that is it. There is no variation. That is what operates in the community. The expected frequency of each group of the categorical variable can be equal or equal. What we mean here is that, for example, now for blood group ABO, the expected frequency is not equal. We already know that O is higher, far higher than other, and A, B, and AB. All of them are not equal. But there are some situations, maybe the expected frequency, you have 4 categories, you expect that to be equally distributed. Normally is 25, 25, 25%. If there are 5 categories, it should be 20, 20, 20. If you divide 5 into 100 into 5 equal parts, give you 20. If it's 4 equal parts, give you 25%. We are not talking of the absolute population, the percentage of are going to each category. For example, now imagine if it has been, I'm just using an hypothetical example. Maybe Nigeria is in 6 geopolitical zone. You may say maybe the employment in the federal civil service, maybe by law, should be equally distributed. That is, when we say all the people that are employed, if we know our proportion come from South, maybe we say it should be 1/6. That is, out of everything should be divided into 6 equal parts. So 1/6, 1/6, 1/6, 1/6 for each of them. So you expect it to be equal. In that situation now, the expected frequency is equal. So, but you want to compare what you have in grant, because what you have in grant will not be equal. You vary, you want to compare it. But in this situation of block group now, the expected frequency is not equal. You are still comparing what you have with what have been on grant. So the way you calculate it, chi-square for goodness of fit is, so you see the table, look at that scenario. I'll be put in the table where I put observed values. So if what you observe in your, this is 70, because there are 300, your own sample size, let's say is 300. What you observe is 76 out of 300 is A, which translates to 25.3%. B, 74 out of 300, which translates to 24.7%. AB, 31, which out of 300, which translates to 10.3%. And O is 119 out of 300, which translates to 39.7%. The theoretical one, the one that had been done before, the percentage in the population is 21.1 for A, 80.9% for B, 15.4% for AB, and 44.6% for O. Are you seeing now? So the one in the population you want to test against, or want to compare your own with, you don't need to know the sample size when you did it that time. You don't even know the, so because if you don't bother to know the sample size, you don't need to know, you won't bother to know what frequency, how many out of the samples are going to each category. But they have already summarized in percentage for you to over 100. So it has been there as relative frequency. You don't have access to their data, but that's what you have read, maybe in the literature or whatever. But you have access to your own. You know that your own sample is 300 here, and these are the number in each category, which you can calculate the percentage. So you are comparing your percentage with the existing percentage. Is it the same? Because you can see some. So the differences you are seeing in the percentages, they are observed difference. The value you are seeing, they are observed value as observed percentages. Now, these differences I'm seeing now, is it due to chance? Or can we say the difference is statistically significant? If it's due to chance occurrence, the probability that is due to chance, the p-value will be so high, higher than 0.05. No, the probability that this observed difference we see, it's just a chance occurrence that it just happened like that. If you redo it now, it may not give the same thing. That's what it means. So you want to put it to test. Is it due to chance? If we put it to test now, if it's not due to chance, you're going to see that the probability that is due to chance will be extremely low, lower than 0.05. Then you now say, oh, no. The probability that this is just chance occurrence is so low that we cannot say it's due to chance. It's really different. That is what we're doing. Now, look at the table, because it's the same formula, Pearson formula you are using. Observed minus sigma, that is addition of observed minus expected, square over expected. So all those 4 categories now, you just do it for it and calculate your chi-square, which you see here. But how do you know? Because you already know the observed frequency for your own something. But what is expected? The expected would be what you expect the frequency to be in the population existing one. If you apply that their own percentage to your own sample size. So if you look at this second table now, so what you now do is the repetition of the other table. We now insert another the expected frequency in another column. So what we now do is, okay, since the expected frequency for the existing one, you know, for A is 21.1%. 21.1 mean 21.1 over 100. You now apply times 300. So you apply your own sample size. The sample size you use for your own, where you derive your own frequency from. You want to apply the same sample size to that one. So you now say, okay, 21.1 of 100, that is 21%, 21.1% of 300. How many will be? Is 63.3. That if you are to apply your own sample size to their own, so the number that we have, A will be 63.3. That's the expected frequency. So that's what you expect if your own frequency is the same thing, the observed, the expected what you expect. If that is, if they are like your own is like their own, whatever, what you have is like what exists before. So for B, blood group B, 18.9 of 100 times 300 give you 56.7. For AB, 46.2. So the value you are getting is frequency, is not percentage now, you know. Then O is 133.8. So now you know the observed before, you now know the expected. You have to feed into the formula. So when you feed in to calculate chi-square, it's 14.464. So the degree of freedom is number of the category minus 1. You know the degree of freedom is one entity minus 1. You know this one is not cross tabulation because you are not having two variables. It's only one variable. You are just comparing. It's just like though it's not exactly before and after, but it's like that because it's the same blood group. You are just comparing. It's the same variable blood group because you're comparing your frequency with the theoretical one. So there's nothing like cross tabulation here. So you cannot say rho minus 1 times no. There are 4 categories. So that 4 categories minus 1 give you the degree of freedom. So the degree of freedom here is 3 because there are 4 categories of blood group, and that 4 minus 1 gives you 3. So you know the critical value for chi-square at the degree of freedom 3 at 0.05 level of significance is 7.815. You check the table, statistical table, one I showed the other time. So if you check it, you see that the critical value is 7.815. Therefore, chi-square 14.464 is statistically significant because it's far higher than the critical value. The implication of it is that the corresponding p-value will be so far lower than 0.05. That shows that the difference you observe is not due to chance, but the probability that is due to chance is so low that, let's say, it's not due to chance. So if you want to run it, the way we do it, this one now, because it's not cross tabulation, it's not 2 by 2 table. You don't go to analyze and now go to cross tab, go to discrete statistics and go to cross tab. No, you go to non-parametric. There's a place called non-parametric test. So chi-square is a form of non-parametric test. So that other one will have been because we will have been here because any chi-square non-parametric test, but because it's work on contingency table, that's why it's easy. Anything that has to do with cross tabulation, they put in one place as cross tab. Not only chi-square, even relative risk, odd ratio, everything, they are under that cross tab. So, but now this one, because it does not use contingency table, will now come to parametric test. Under it, you now choose legacy dialog. Under the legacy dialog, you go to see chi-square. You click on it. When you click on it, it gives you this. You'll be able to push OK. For that variable, test variable is a block group. So it will give you for each category of, look at this first option on the right side down, you see expected value. You see there are two options, all categories equal. If you click all categories equal, if there are 4 categories, it means that the category should be equal, divided equally for the expected value. That is, if there are 6, if there are 4 categories like this, 25%, 25%, 25% will be there. So, but if it is no, you put the value. So that value you enter a one by one. For you arrange according to the way like for this one, A, B, and O. So you now put the expected value and be entering it. You'll be adding. That's how that in 63.3, 56.7, 46.2, 133.8. Those are the expected value we calculated for each category. When you do that, you go, it run it. Can you see? It brings you something like the table we had before. You put your observed frequency, the expected frequency, the residual. Residual is, that is, when you remove this from the, when you remove expected from this one, look at it. When you remove 63.3 from 76, it gives you 12.7. When you remove 56.7 from 74, it gives you 70.3. When you remove 46.2 from 31, it gives you minus 50.2. When you remove 133.8 from 119, it gives you minus 4.8. If you look at it, if you try to add it, it will be 0. Can you see? I was telling you yesterday. That is the logic behind squaring it also. Now I told you. That is, when you remove observed from expected, some observed will be higher than the expected. Some expected will be higher than observed. So when you remove expected from observed, it will give you positive with some, it will give you negative with some. But if you try to add it, it gives you 0. So now that's the logic behind squaring. So that was some, but the computer doesn't, they have already programmed it. It just give you the answer. It's no, you are not using hand to solve it. Can you see? The same value 40.464. And the degree of freedom is 3. And the p-value, can you see, is 0.02. You see, you cannot calculate the p-value with hand, but the computer will calculate it for you. You know, you can only calculate the chi-square with your hand. You cannot calculate the p-value, but the computer will calculate both for you. So can you see? We already know that once the chi-square value is far higher than the critical value, the corresponding p-value will be far less than 0.05. That's what you see now. 0.02 is less than 0. In fact, it's 0.002. That's what you have there. 0.002. So any question? So that's the end of chi-square for goodness of fit. So we'll go to the next one, which is Mach-Nemmar chi-square. Any question on that before we move ahead? Is that people are cooking, they are not in this class. Is it so clear?
This class,
we are with you, sir.
Okay, no question, right?
No, the question I want to ask, sir.
Okay, sir.
Do we have to know all the degree of freedom of and?
No, you don't need to. No, you see, sir. No, even you don't know degree of freedom. Even you are solved yourself, you don't know offhand. Degree of freedom is not something there's nothing you even know offhand here. Apart from, to be sincere with you, apart from the formula for chi-square that you need to remember. If you want to solve with hand, you don't need to remember anything, because what you can, what you need to remember about degree of freedom is that the way you calculate it. If it's for this type of goodness of fit, it's number of category minus 1. If it is for anything that has to do with contingency table, where you cross tabulate, it's going to be number of row minus 1 multiplied by number of column minus 1. That's all you need to know. Because by the time you are faced with those, you'll be able to calculate them. It's you that will calculate them from. It's not that you say the degree of freedom here, you cram in. No. For how many scenarios will you cram the degree of freedom? You don't need to know it.
You know, you are trying to compare the degree of freedom for 1, degree of freedom for 2, and then you compare it with the value that
No, it's not the degree of freedom. It's what I was comparing is observed value and expected value now. Are you talking of?
You mentioned that the value of degree of freedom at 3 is so and so, and that's what you compare with when you know the degree of
what I'm saying. Okay. This is where you are talking about. Where I
The
say
value of each of these degree of freedom.
yeah, you say the critical value of chi-square.
Yes.
No, this
Yes, sir.
one now is not offhand though. It's me that I've checked it even from my own. I check it on a statistical table. You know. I've gone to when you
Okay.
solve, you go to statistical table of chi-square. You now say, okay, degree of freedom 3
3 is
at
so and so.
0.0 level. What is the corresponding chi-square? Let me go to that place where we, when we show chi-square, a section of chi-square, and look at it. Statistical table. Can you see?
Yes.
Examiner.
This is
Here
the
now,
area that.
it's not confusing now. First of all, look at that graph up. That graph
Yes, sir.
is chi-square. You know it's skewed. Chi-square is skewed. It's
Yes,
not
sir.
normally distributed. It's
No, no,
usually
no.
skewed to the right. Then
Yes,
the
sir.
area under the graph is all one. All area of any statistical something, any graph is one. One just means 100%. So now, what we are looking at here is that we say that the level of significance, it corresponds, is a complement to level of confidence. So if you have 100% now, that's total.
Yes, sir.
If you say at 95% confidence interval or confidence level, your level of significance will be 5%, the remaining to complete 100. So that's how you say
Yes.
the level of confidence and level of significance add up to 100. So that
Yes, sir.
graph, what is showing you, if the total area on the graph is 100%, if you
It is one.
have a line, you need a point that will show you on the right side 35% area, the
Yes,
remaining
sir.
5% area on the left side. That point, if you are moving from, the value of chi-square is along the horizontal toward the right, from a zero along
Yes.
like that. So as you are going, what is the value of chi-square that corresponds to the area where you, at a point where you have 95% of the area on the right side, the
Yes.
remaining 5% on the left side?
Yes,
You
sir.
get the picture now?
Yes, sir.
That that particular point of the chi-square
Point. Yes, sir.
is the critical value. It's
Yes, sir.
specific for a particular degree of freedom.
Yo, freedom.
So,
That's the area.
so you have to first of all know what is the degree of freedom I'm looking for. But in this case now, the one we just calculated for this, what do I
The
call
degree
it?
of
This
freedom is
video
3.
blog group now, we have known the degree
Yes.
of freedom is 3. Do you get the picture
Yes,
now?
sir.
So
Yes, sir.
now, it's not only that. You know that they also translated this graph to the table. You see, the green part of the graph is the 1 minus alpha. Alpha is the level of significance, which 1
Yes.
minus alpha is the 95%. The
No.
Bible shows 95% anyway. So either we choose 95% or 99%. So now let's go to the table. The green area where we have 95%, if it's 95%, we choose. Your level of significance will be 5%. Can you see now? Look at this green
Yes, sir.
area here now. It's
Yes, I can see.
0.95.
Go
Look at
ahead.
the
Yes.
corresponding level of significance is 0.05, which is the remaining 5%. Can you see now?
Yes,
If
sir.
it is 90% confidence level, the other one will be 10%. Can you see?
10%.
If
Yes,
it's
sir.
75%, the other one will be
It's
25%.
going to be
If it's
25%. Yes.
25%, this one will be 75%. Each one is
25%. Yes,
10%,
sir.
this one 90%. But all this one, but if it is 99%, the other one will be 1%. It's 0.1. Can you see now? So but
Yes, sir.
most of the time when we are doing our judgment, we choose 0.05, which is 5%. So that's why if you come under 0.95, which is 99%, 95% confidence level, and 0.05, the blue area, which is level of significance. Look at the critical value. For degree of freedom 1 is
1 is 3.
3.841. For
Yes, sir.
degree of freedom 2 is 5.991. For degree of freedom 3, 7.815. So for this one, we just calculated now, which is this, because we know that there are 4 levels of ABO and 4 minus 1, 3, make it 3
3.
degree of freedom. So we now, the
Yes, sir.
critical value for chi-square is 7.815.
815. Yes, sir.
So when we calculated 40.4 something. So our own, what we calculated is far, far higher than the critical value for that degree of freedom.
Yes, sir.
We now know that the corresponding B value will be less than previous operator. It should be significant. Does it
0.1.
make
Yes,
sense
sir.
now?
Yes, sir.
Yeah.
You've answered my questions, sir.
Okay, that's
This value are the one I was asking that one I need to cram it or
no, you
don't
don't
need
need to
to
cram
read
it.
over.
You don't need, in
That's
fact,
three
if you
point
are
eight
if
four to
you
five point
no,
two.
you don't need to cram it. You don't need to cram it because if like now, even my postgraduate student, undergraduate, postgraduate, we give them normally they are supposed to come with their statistical table. But I actually
Table.
print
Okay.
if I ask question about chi-square and ask question about t-test and over, I will also actually attach the statistical value to their question. I
Okay, sir.
will attach this thing to their question. I actually
Okay,
bring
sir.
together in one page. You know, this one is very short. I just put it then with the t-test. I put it one table and print it one page on their question also. So
Okay.
they at the back of their question, they can check if they
Okay, sir.
want to check. No, you can
Okay,
you
sir.
don't need to cram it. You just want
Okay,
you to
sir.
go and
That's
check. Yeah.
thank
For
you so
exam
much.
purpose. But for your own without exam, you don't even need it because computer give it out. You don't need to go and check anything. So as I've run it now, you see that
Yes,
the
sir.
information is out. The p-value is out looking at you. So
Ye-
you don't need to
Yes, sir.
check anything. So look at
Okay,
it.
sir.
Look at it. Look at it. You give us the p-value. You give us the. You don't need to know. Even the degree of freedom, you give it to you. The examiner.
Thank you, sir.
It's only
Yes,
that
sir.
in an exam, if somebody is going for exam, they want to. How do you calculate? They can ask you. How do you calculate? What's the degree of freedom? You must know the logic behind it. Or you are an examiner. How do you assess? If you don't know, how will you assess the something? All your students see the degree of freedom. You may want to pick.
That's important. That's why we are learning that.
Yes, you now say how do you calculate the degree of freedom? You know, it depends if the student does not know. Now know that the student does not know the logic behind it. Okay,
Okay.
so
Yes, sir. Thank you so much.
we
McNeil.
go to McNema chi-square. McNema. So they are quite interesting. Maybe we still have time. We should continue or should we stop here? Because after a while, some people cannot absorb some things. Should we continue? We have treated two now. Should we continue or we stop here?
Stop here. It's 9 o'clock on the dot. Maybe we can stop here.
Is that consensus?
Thank you, sir. I think it's okay, sir. We can stop here.
Okay. So, yeah, I know that when it comes to all the issue of this thing, it can be so, you have to be dishing out those by small, small, little by little.